So we'll follow along that. Let's go ahead and get started. Go to the Start menu, ANSYS 2023 R1. Go down to Mechanical APDL Product Launcher and create a unique working directory and job name. All right, so I'm going to, under My Documents, Section 2, Assignment 3, call it Assignment 3, and go ahead and click Run. All right, so we're going to define our elements first. It's going to be the beam 188. So go to preprocessor, element type, add, edit, delete. Click add. And then you want to come down to the third item here called beam. And then on the right-hand side, you want to click on the 2-node 188. You'll see the one below it is a 3-noded 189. This is the same element, but it has a mid-node. So between I and J, the 2 nodes on the ends, you have a third node in the center. Typically, when you're conducting these simulations, you want to use the highest order element you can get away with, which would be the 189. But for this assignment, we're going to use the lower order one. So leave it 188, OK, close, and then go up to the command prompt, and let's read about this element. So type help, comma, the element number, which is 188, enter. All right. So this beam element is not a 2-force member anymore. We now have rotational degrees of freedom at the nodes. So that means it can support a moment applied to it, and it can support a shear stress on it. So 188 is suitable for analyzing slender to moderately stubby/thick beam structures. The element's based on this Timoshenko beam theory, which includes shear deformation effects. And let's keep reading. Next paragraph. The element is linear, quadratic, or cubic 2-noded beam element in 3 dimensions. Beam 188 has 6 or 7 degrees of freedom at each node. That's a lot of degrees of freedom. If you recall from lecture, our current truss element, it's in 2 dimensions. It has 2 degrees of freedom per node, right? So now this element all of a sudden has 6 degrees of freedom per node. The degrees of freedom are translation XYZ and rotation XYZ. So there's a rotational degree of freedom at each node. If you look below here, here's the image of the element. Here's node I. Here's node J. Right? So it has 6 degrees of freedom at each node. So that means the stiffness matrix for each element is a 12 by 12 matrix. Our stiffness matrix for our 2D truss element is a 4 by 4. So this stiffness matrix is pretty big. If you scroll to the very bottom, you'll pass some things that may be important to point out. We need to specify now the cross section of the beam because we're accounting for the bending stress and the shear stress inside of the element. So we'll have to get a cross section. So for the I beam, we'll get an I beam cross section, and then the box beam, we'll give it a square cross section. Let's go to the very bottom here. A couple assumptions. We don't need to read all these. The beam must not have 0 length, so it has to be between 2 two key points that are at the same location. Cross-section failure or folding is not accounted for. You can't fold these beams in half, crease them. What else? Only moderately thick beams can be analyzed. So you can't really model like a beam which is really fat, but very thin. In those scenarios, we should use either a solid element or a shell element to do that. So we're mainly dealing with these structures that have a much larger length than do their diameter or width. They call it a slenderness ratio. We'll talk a little bit about that when we get to buckling. Okay, so that's 188. 189 is a mid node on it. We can pull that up too if you go back to ANSYS. You type help, comma 189. This is the higher ordered version of the beam elements. It has an extra node here, node K at the midspan of the element. So it's good for if you have like a high curvature on your structure you're trying to mesh. You can get away with a coarser mesh by using this version as a mid node. And this can mesh things better with less number of elements. Okay. Let's come back to ANSYS. So we got our element type in there. We need to define next the material properties. So we're going to define two material models, something new we haven't done previously. We're going to have one for the I-beam and one for the box beam. They do have the same EX and PRXY, Poisson's ratio, but they have slightly different densities. It has to do with the standard that are used to manufacture these. So 836 density is a little bit different than A500, and their yield points are different, which we also need to consider. Okay, so let's come out of element type. Let's go down to material properties, go to material models. So here's material model number one. We'll use this for the I-beam. Let's go over the structural, linear, elastic, isotropic. Click on that once. Let's specify EX to be 200 e to the 9. So convert a gigapascal to a pascal. And then Poisson's ratio is 0.28. So 200 e to the 9 and 0.28. Click OK. So this material model is this modeling the linear elastic region of the stress strain curve. And then we want to come out of linear and go down to density and also add the density. So we got to look up this density value. I'm going to tell you what it is. It's 7850 kilograms per meter cubed for 836, 7,850. Click OK. You should have density and linear isotropic for material model number one. So we're going to use that for the I-beam. Let's add a new material model for the A500 square tubing. So go to material up here, click new model. Click OK when it says define material ID 2. You'll see material model number 2 show up here. And we want to add these same ones again. So let's start with linear, elastic, isotropic. It's going to have 200 e to the 9 and 0.28 for Poisson's ratio. So exact same stress strain curve. Okay, but the density, so add density now, is going to be a little bit different. It's going to be 7,800. 7,800 kilograms per meter cubed. All right, so you should have two material models, and then density and linear isotropic into those. If you ever have to change these, you can just click on them. So if you want to change the density, you know, just click on it and then change that value. Click OK. All right. So go ahead and exit out of that. Let's go to matweb.com. So matweb.com in the browser. How many people have been to matweb.com? One person? Baha?
I think I had to do it for my capstone.
Capstone, okay, yeah. Yeah, this is a nice website to look up material properties. It's basically a catalog of different steel manufacturers' material properties. If you pay for the premium membership, you can actually import these properties in ANSYS. But if you don't have the premium membership, you can just type up here in the search the material you wanna find the properties for. So let's start with A36. Right, so this is the ASTM standard of steel. See right here, we want to click on the steel flange right here. And here's the properties in metric and English units. Sometimes they'll give you some nice notes up here. This one they say steel for general structural purposes, including bridges and buildings. You can see what they add to it. Has carbon in it, 0.29% carbon. Has a little copper in it, mainly iron. Some magnesium, phosphorus, silicon, and sulfurs in there. Right. So it's like a mild steel. Has good ductility in it, so it doesn't fatigue, and you can see the failure in the material. But we need the density. That's one thing. So it's 7.85 grams per cc. If you convert that to a kilogram per meter cubed, it's 7850, which is what we typed in. We need the yield of the material. I'm just going to write these down in Excel so we have these. Sigma Y. 836. So yield is 250 megapascals. You'll notice the module's fuel elasticity is 200 gigapascals. Strain to failure is 20%. Which is decent ductility, right? The reason I want some ductility, so like if somebody overloads the bridge, right, it's gonna plastically deform. You know, it'll get a hump in it. It won't catastrophically fail if somebody overloads it, right? Also, ductile materials typically can arrest cracks if there's a crack in it due to fatigue. Somebody can come and inspect the bridge and see if a crack has started. If you have a very brittle material, yeah, it'll have a higher yield stress. But often when you get cracks in these materials, they'll shoot through the material, you know, catastrophic failures. Typically, for most materials, you want to have some, you know, that are dealing with potentials to overload. You want to have some ductility in them. All right, so that's sigma y. We can write down rho 2. It's a gram per cc. 7.85. Let's look up A500 now. You go back up to the search A500. You might be wondering, like, how do I know it's A500? Well, it depends on the supplier, right? So if you call Huntington Steel up, you just can't order steel tubing in any grade steel, right? The steel that you're going to get is what they produce, which is A500 for square tubing. This is shaped structural tubing. Here's the density, 0.780. Same thing with the I-beam. You just can't order some random material in I-beams. It's whatever the supplier manufactures for these I-beams. We need the yield here, 270 megapascals. So it's a little bit higher on the yield. You'll notice it has a little bit. They can have a little bit more carbon in A500. The standard allows that. It says less than or equal to 0.3%. Has a little copper in it. It's mainly iron. They don't add any phosphorus or they don't add any magnesium to it. Yeah, you'll see it has A36 is a little more magnesium to it. I think it helps with the ductility. What was the ductility in this one? Okay, so those are my material properties. We need to get consistent units on rho. We already told you what those are, but we need kilograms per meter cubed as our units because we're going to plug in the force as a Newton, and then our length is going to be in meters. So it ends up just being that value times 1,000 is our density for both those. Okay, so let's go on to the next step, which is we need to define the sections, the cross sections of the beam. So this is a new step we haven't done before. So preprocessor sections, common sections. So sections, we have to go to beam, common section. We get the beam tool. Let's type in the name I-beam. Let's change the subtype to an I shape. This. You'll notice below you get a figure of an I-beam. We need to give it W1 through 3 and T1 through 3. All right, so W1 is the width, W2 the width of the bottom flange, W2 is the width of the top flange, W3 is the depth of the beam, and then T1, T2 are the thicknesses of the flanges, T3 is the thickness of the web. So if we had our strength and materials book, we could look in the back of it for these dimensions. What we're going to do for this time is just Google it. We got to look up a W10 by 112 beam. The W indicates it's a wide flange beam. The 10 indicates, does anybody know what the 10 indicates on the designation? So the 10 is the depth of the beam. The 112 is the pounds per linear foot of the beam. So if you knew you had a 10-foot section of this I-beam, you would know it weighs 1,120 pounds. So this is in English units. We need to convert this to a meter too. Let's see if we can find a better. So here we go. So we got BF, TF, Y, BF, TF, TY, TW. All right, and then this is D is the depth of the beam. So we got a W10 by 112 right here. Right. So here's the depth, 11.36 inches high. The width is 10.415. That's the thickness of the top flange. This is the thickness of the web. But we need to be careful. We need to convert 1 inch to a meter. So we need to multiply all these numbers times 0.0254. Okay. So let's start with W1, which is the width of the flange. Close, I saw it. 10.415. 10.415. 10.415 times 0.0254. W2 is going to be the same, 10.415 times 0.054. W3, 11.36 times 0.0254. Thickness is 1.25 for both the flanges. So T1 and T2. 25? 25 times 0.0254. 1.25 times 0.0254. And then 0.755. 0.755 times 0.0254. Once you have that, click Apply, and then click Preview. Move the beam tool off to the side. So there we go. So we got an image of our I-beam. There it is. If you'll look to the right, this is the area, and meter squares are units. Moments of inertia, centroids at the center here, and then the shear centers are also at the centroid. You guys remember calculating shear centers from aerospace structures? How many people want to calculate the shear center from hand right now? No? Yeah.
When the window goes away, how do you do that?
Yep. So if you ever lose the window from behind, like this, click Raise Hidden here. bring it back up. Did it work? Yeah, so because it's a symmetric cross section, right, the shear center is at the centroid. If we had half the I-beam, it was a C section like centroid, the shear center be the same.
It says that's a little negative there.
Huh?
Giving me a weird error.
No, I see the flaggers.
I just walked in, didn't turn my lights on. Just like,
Yeah, that's
I took off my dress pants and put on sweatpants. Left my sweater on. And slept. And then when I texted you guys this morning, that's when I woke up. I know, I just don't really get in the habit of missing class, but like, I was doing Sam. I got home immediately last night, took off my dress pants, put on sweatpants, didn't turn any lights on, just went off. The lights never, I didn't turn a single light on. You know how bad is when I don't fall asleep with my lights on. Like, that's like the, like, I don't turn on a light. That's bad.
So I ran out of space here,
That's
but
really bad for me.
did it work? So the question was, you had a C channel. Is the shear center the same as the centroid? You think? What do you think? How many people think it's the same? C channel. Shear center is the same as the centroid. No, it won't, right? So if you load it up, it'll twist. So for those of you who didn't take aerospace structures, shear center and the shear center and where the load is governs where how it twists. I assume that's aerospace structures you
Yeah.
today.
It is.
Yeah, why don't we taught this? You do it by hand.
Yeah, you do it by hand. If you knew ANSYS, you could have it calculated because you can actually import custom cross sections too, and it'll calculate for you.
That would have been so helpful.
So we go through this entire degree crying and then we get to this, oh dang, never have to do that again. Well, we learned how to master Excel.
Yeah, so one thing I've done is I made like I made a beam in SolidWorks, and you can export the cross section from SolidWorks, bring it in the ANSYS, and have it calculate the shear centers for you in the centroid of it. Okay, so that's the I-beam. Let's change the ID here to 2. It should reset everything to blank or to defaults. Let's type the name in as square So the square cross section. Change the subtype to the square. Okay. And now we got to give W1, W2, and then the thicknesses. So W1, W2 are going to be 4 inches. So 4 times 0.054, 4 times 0.0254, and then our thicknesses are 1/4 inch all the way around. Okay. And then click apply. Once you get that, you can click preview again. Okay. You get a preview. Shear center, centroid is the same, again, it's symmetric. Yep.
Why offset Y and offset Z have values in it? Is that screwed up?
Offsets.
Like under the centroid.
Put it back as centroid. Did you switch it? Did you switch this at all? Or?
Yeah, it's still there.
So you put centroid. Can you type in these boxes?
No, hold on, yeah. Figure it out.
So one other thing we can do is there's this slider here from course define. If you hit mesh view, it'll break the cross section up into a series of rectangles. Actually, rectangles and squares at the corners. And then if you scroll this up, to fine, and then you click mesh view again, you get a bunch of rectangles and boxes. So this is the mesh in the cross section. So each one of these rectangles and squares are where the stress is going to be evaluated in the cross section. In the case of linear elastic analysis, we're not going past the yield points. The fineness of this mesh really doesn't matter. But if you ever had a scenario where you go past the yield point and you start to plastically deform the object, you can figure out where the yield surface is. It's going to yield first at the outermost fibers, so it's going to be like this. It'll yield most at the outermost fibers. And then that surface, the yield surface, is going to go down. Right? You can figure out where that is if you put enough mesh cells in the cross section. So we're not doing anything that complicated, but it's possible to do that in software. So we're just going to leave everything as coarse. We don't need that many mesh cells in the cross section. Everything's going to be elastic, and we're mainly interested in what's the stress in the outermost fibers. Okay, so we got our 2 cross sections. Go ahead and click OK on this window to close out. And let's start building the structure now. So what we're going to use are key points again. And then we need to make sure we put a key point at the load point. We need to put a key point 2 feet above that load point for orientation point. And then we're going to create straight lines. So kind of a different approach than we used last 2 labs. So let's start with our key points. If you look at the figure, we're going to define this point as the origin point. Notice things are in feet. We need to convert these to meters. So we'll go inches, convert to inches by multiply times 12, and then we'll go to meters. All right, so there's going to be no point at the origin, but the first point is going to be right here. It's going to be 2.5 feet in the negative x direction. All right, so we're going to go down to modeling, create key points in active CS. Go ahead and type next in for the key point number, so we don't have to manually increment this. It'll auto increment. Okay. And we're going to go negative 2.5 feet times 12, which will get us in inches, times 0.0254. And then we'll put 0 in for Y, 0 in for Z. Okay. So click apply to keep the prompt open. And now let's go get rid of the negative in front of 2.5, go positive 2.5, hit apply. All right, so that's our bottom of our A-frame right there. Now let's go up to these 2 points. They're 5 feet in the Y. And then oh shoot, I lost my dimension in here. I think it's 1.458. So go negative 1.458 in the X, and we want to go 5 times 12 in the Y. Let's see if this is right. Hit apply. Oh, thanks. Okay, so now put 3 in here. If you clicked OK, put 3 in there. And then click apply. Then do fit the view over here. Let's bring it back. Okay. And then change the 3 to next. It'll go to the 4 now. Now do the positive 1.458. Hit apply. All right. So there's our and then let's do 0 in the X, but now 12 feet in the Y. So 0 in the X, 12 times 12 times 0.0254 in the Y. Click apply. You click fit view over here. You can see it. It's looking good. I'm clicking raise hidden too. When I click fit view, it goes behind. Click raise hidden and bring that back up. Okay, and now we need to go along the I-beam to this point, which is 9 feet in the Z direction. So for the Z, do 9 times 12 times 0.0254. Click apply. Okay. And then we need to add that orientation point at 2 feet above that point in the Y. So make that one 14, make the Y 14 times 12 times 0.0254, and then on this last one, click OK to close the prompt. Okay. And then go ahead and click Fit View here, the magnifying glass with the cube, and then hold Control on your keyboard, left Control, and the right mouse button. And rotate it so you can kind of see all the points there. So you can see the A frame. You can see 0.6, and then 0.7 is right above it. I can go to List Key Points, show you my coordinates too, if you'd like to see my coordinates. If you need to adjust any of your points, you can just go back, click Inactive Coordinate System. Yeah.
Was that last one, was it 9? Other thing to see was like 9 times 12?
Yep, 9 times 12. And then I moved it to 14 feet in the Y. So if you need to adjust any of these, you can go back to Create Inactive Coordinate System, and you can type in the associated key point number here. So if I want to move 7, I can move the 7. Okay, so those are our key points. Now let's draw our lines. So go back to Create, go down the lines, straight lines, and then start connecting the key points. I'll go 1 to 2, 2 to 4, 4 to 3, 3 to 1. I can go 4 to 5, 5 to 3, and go 5 to 6. And then click OK. So no nodes and elements yet. These are just guidelines that the software create the nodes and elements for us. Okay. Any issues there? If you scroll in and out of your model, you'll lose the lines. The reason why you lose them is because it's in points plot, your refreshed points plots. If you want to see the lines and the points, go to Plot, Multi-Plots, and it'll plot the lines and the key points. All right. And if you want to add back in the key point numbers, you can go to Plot Controls, Numbering. And the first control is the key point numbers. Turn that on. Okay. You can get your numbers back. Okay. So what we're going to do now is mesh the lines to generate the nodes and elements. Before we do a mesh, we need to specify the attributes for each of the lines. And the way we do that is we go to Meshing, Mesh Attributes, and we specify the attribute. We'll start with the A-frame first, and then we'll do the I-beam. All right, so we're going to come out of modeling, go down to meshing, go to mesh attributes, and then come down to pick lines here. And let's pick all the lines that represent the A-frame of the structure. 1, 2, 3, 4, 5, 6. Your count should be 6. Click OK. All right, and we got to remember which material number. We should have two options here. Which material model was A-frame? It was material model 2. And then we also need to set the element section to square. Right? If we don't change that one, we'll get I-beams for the A-frame, which is not correct. We want the square 2-beam. So do 2 and 2 for that. Click OK. Go back to mesh attributes, pick lines, and now pick the line that represents the I-beam. Click OK. And you want to make the material number 1 and make the element section 1. And then before we exit this, we need to pick an orientation key point. So turn that on, yes. And again, the reason why we need that is for to orient the I-beam so it's vertical. If not, we'll get the I-beam on its side, which is not the correct orientation. Okay, so you click OK. You'll get this prompt. It says pick key points for orientation. You want to click on 7, key point 7. And then click OK. All right. So next thing we want to do is specify the element edge length size, that it'll divide each of these lines up into elements. So go to size controls, manual size, lines, all lines. And specify the element edge length to be 24 inches times our 0.0254. Notice there is an option to number of element divisions. If you read the parentheses below this, ended is used only if size is blank or 0, so you can't do both of them. You only specify what the element edge length is or the number of divisions.
I got where you select make it square with the section.
It's so bare minimum to get $500. The devil. And they love you for it. It's a problem.
Like that one.
Street that is our inside. Because, give me a second, hold on, you wanna see why you can't say that? This one right here automatically populates from the list of stuff, and the red tells who hasn't done the background checks. I can't do that, I'm locked out, but the only two who have access to it is the ignore. They won't. Because legally, if they do that, then they can be fired, so they are liable to have a background check when people. Start shit posting.
All right, so go ahead and click OK on this, and you'll get a preview of the mesh. So we haven't created any nodes and elements yet. These are just the preview. It's just a preview of the mesh. All right. And now we need to actually mesh it. So go back out of size controls and go down to mesh, lines, and then do pick all. And it'll put you in element spots. Here's what it looks like. You can turn E shape on to take a look at it, make sure everything looks good. So go / E shape, comma 1, comma 1. / E shape, comma 1, comma 1. You can zoom in and out to refresh the plot. That's what it looks like. So if you didn't define the orientation key points, your icon will be on the side. Anybody have that issue?
I did that. Now back to chair. I have it on the site, and it's businesses. If I have to look
I actually want to take like a Python course. There's a free one that's offered by LinkedIn, but it takes me a while to do it.
Yeah.
It's not like in this summer issue. There might be a cross because when I get home from work also, in my hotel room I do that. So I don't know, like, I don't know, put it on there, it's like, I've used it more than once and I could like kind of stumble my way through it probably. See, I've never used Python. I used Python once and that was for physics 111. I've used it once, I don't remember how. I'm also like 90% sure it's to like get my projectile thing to work, so I'm like off of like a tutorial online.
Yeah, probably.
Yeah. So she's like, use Python for it. Didn't she just have to use Python? I like her though. I like her child. I like her so much better than John Stewart. John Stewart's good. Yeah, and then she was having kids. Yeah, I know, because I took that section of 112 for her. You want to know that shit?
Me?
Yeah. He was in our section. Yeah, there were because Maddie took those honors. I didn't take 112's honors, but Maddie did them. We were all in the same class. We were in the same lab with Brooke and Nathan. I saw Nathan in the hall the other day. Others, we have our own Nathan. We have Nathan.
Is he? And sometimes you say
I always thought he was. Maybe it's because whenever we were graduating, he said that he was doing EE, and then he changed his EE when he got here.
That's the one that I'm saying about whenever we spot on this, you always say EE.
I know. That's what we were talking about. I was like, "Are you ready to be done?" He's like, "Fuck yeah." Well, the other thing is too is that Sarah's been done. She graduated last spring. She did the OT stuff in 3 years, and now she's doing the master's for OT right now. So she'll be done and have her master's when he graduates with his bachelor's.
It's funny about the lines. That's full discussion. He asked me, hey, I'm stats. I like this one. He's like, he didn't know. He's like, I'm stats. And I was like, pretty easy. And I was like, well, and then I texted him back like 5 minutes later. Wait, you do too much bulk that fast. You're not going to get it when I left. It's like,
It's entirely too much. Just because it's a 200 level course doesn't mean you should take it as a tech lesson.
I was like, I don't think it's that good. It's too much block. It's concept. It's stuff that is like,
The concept stuff is easy. It's just a lot of fun.
and then he's like, I was like,
All right, let's keep going. So we got to put our boundary conditions on next. What I'm going to do is I'm going to turn the E shape off for a second. So again, do a / E shape, comma 0, 0, enter. And then zoom in and out with the third mouse button. You'll get back to the lines. Okay, so we got to put UX, UI, UZ equals 0 on the key points down here on the bottom of the A-frame. Let's work on that first. So come out of meshing, go down to loads, define loads, apply structural displacement. And then you'll see 2 options you can basically do. You can do either on key points or on nodes. If you have the option to put it on key points, it's better because if you put it on nodes and you remesh, you clear your mesh out, it'll delete your boundary condition with it. Because we never delete the key points because it makes up our geometry, if we apply the boundary condition to the key point, they'll never get deleted when we remesh. So I suggest using on key points. And then you want to click the 2 key points that are at the base here that represent the casters. Click OK. And then for our degrees of freedom, what we want to do is we don't want to do all degrees of freedom because it'll constrain the rotational degrees of freedom. That would be as if we're cementing this thing in the ground and get a reaction moment. We're cemented in the ground. So we want to treat them like a pin joint, basically. We only want to restrict UX, UI, UZ, but we want to allow it to rotate, right? Because the caster can still pivot on the ground. It's not like always vertical. If that makes sense. If we had this crane, on pylons that were cemented in the ground, then we would get a reaction moment. In that case, you would want to restrict the rotational degrees of freedom. Okay, so we just want UX, UI, UZ, and then we want the displacement value to be 0. And then click OK. You'll get the 3 displacement constraints. Next, we got to put a displacement constraint at the symmetry wall. So go ahead and go back and go displacement on key points. Click on that point that's on the symmetry plane. Basically, we don't want this plane to come off the symmetry plane. We don't want to move off the symmetry plane. So we want to restrict UZ. So click OK. Turn off UX and UI. So we still want the point to move down on the plane in the Y direction. And we'll still allow it to move in the X, which would be this direction on the plane. But it's just not going to be able to move off the plane. So make sure you just have UZ there. Click OK. We'll get one little support. And next, we got to do the rotations on that point. So go back and click displacement on key points. Click OK. Click that point 6, key point 6 again. Click OK. We could have done this on the previous step. Okay, and we want to restrict rotation in the X. Okay. We want to allow rotation in the Z, and we want to restrict rotation in the Y. Right, so you got to imagine you just cut the I-beam. Here's my symmetry plane. I don't want it to lift off. If I rotate this way, I don't want it to lift off. It's okay to rotate this way. That would be the rotation Z. This would be the rotation of Y. We want to restrict that. And then rotation of the X would be this way. We want to restrict. So we want UZ, rotation X, rotation of Y to be 0. Click OK. There you go. All right, so those are our boundary conditions. We now need to add a force that represents the engine we're picking up. So again, go to apply structural force/moment on key points. Let's click on key point 6 again. Click OK. This force is going to be in the negative Y direction, so do Fy. And then it's 5 tons, which we need to convert to a Newton. So 1. Some metric ton. Let's do tons. That's right. We'll call it 9,800 newtons. So 1 ton is 9,800. So we got 5 times 9,800. And we want that to be in the negative direction, so I'm going to do a negative out front there. So negative 5 times 9,800. Then click OK. should be in the negative direction. And then the last, oh, wait. We forgot our multiplier, 1.35. Right? Because if you look back at the assignment sheet, we've got to do, where's our equation? We need to do 1.35 times the live load. So let's redefine that. Structural force on moment on key points. Just go back and click key point 6 again, okay, and multiply it times 1.35. And then click OK. All right. And now we got to add gravity in. So structural inertia, gravity, global. And our multiplier on the gravity or dead load was 1.25. So we want 1.25 times 9.81 meters per second squared. Right, and that's in the positive direction to get a negative gravity vector. So click OK. 1.25 times 9.81 in the y direction. And now we're ready to solve this. So go to solution, analysis type, new analysis. We really don't need to change anything here. It defaults to static structural, so we're just going to leave that as is, okay. And now go down to solve, current LS, and then click OK. If we did everything correct, we should get solutions done. And then we can go down to general post-processing, plot results, deformed shaped. Let's look at the deformed. What's undeformed? And we messed up one step. Does anybody know what we messed up on? I did this on the last lap too. No. So the thing we messed up on is we're simulating half the structure in it. So we should put half the load on it. So we need to go back and redefine the force. So that's pretty easy. So let's go ahead and do that. Preprocessor.
Yeah.
Go down to loads, define loads, apply force / moment on key points again. Click 6, key point 6 again. And we want to do a divide by 2. And the reason why we do this, if we were in full symmetry, if we had the full structure there, we would do the full force. Because we're only simulating half the structure, we need half this force. All right, so divide by 2 on that. Let's go back and resolve it now. Solution, solve current LS. Click OK. And now let's take a look at the formed shape. This is what the deformation looks like. Again, it's exaggerated. The deflection is only 4 millimeters, 4.4 millimeters, 4.5 millimeters. And again, the units on that are meters. So if you multiply times 1,000, move the decimal over 3 places, you're in millimeters. It's displacing 4.4 millimeters. All right. Let's take a look at the stress contours. I'm going to come out of plot results, go down the result viewer. Where it says choose results, I'm going to click on nodal solution and go down to element solution. Stress. And I want to find von Mises stress right here. And then click the plot results button. And you'll get a red contour. All right. The reason why we can't plot the contours of the stress is because we don't have E-shape turned on. So I'm going to exit out of that, come back to my command prompt, / E-shape, comma 1, again. Turn on your cross sections. Now go back to result viewer. Plot me some stress. Plot the stress now. So this SMX is the maximum stress, the minimum stress. This is displacement max. Right. So notice we're getting 42 megapascals. So the stress, our yield point is at 250 and 270. So we're okay. Okay, so that's our first result. Let's what I want you guys to do is I want you to look. I just want you to watch me do this quickly. So I'm going to iterate the mesh a couple times, and I want you to watch the values when I do this. You don't need to follow along. You just need to watch me. So what I'm going to do is I'm going to half edge length, right? So currently we have each element is roughly 2 feet long. So I'm going to make them now a foot long. The way that I do that, and again, just watch up here. Don't do this to your model. As I'm going to meshing, I'm going to clear the mesh first. So I got to clear lines. I pick all the lines and clear them out. I'm going to go to size control, manual size, lines, all lines, and change that value of 24 to 12 now. Click OK. Come out of size control, go down the mesh, lines, pick all the lines, and remesh it now at 1 foot edge length. And if I turn E-shape off, I can show you that the boundary conditions are still there because we put them on key points, not on nodes. So if I go plot controls, symbols, all applied boundary conditions. Sorry, I got to go to multi-plot. You can see the boundary conditions are still there. All right, so that's the advantage of putting my key points, because as soon as I cleared that mesh out, I get rid of all the nodes in my simulation. If I had any boundary conditions on there, they would also get wiped away. Okay, so I changed the mesh. Let me rerun this. Let's take a look at the results quickly. So there's my next result. Let me make note of the numbers. I'm going to calculate a percent difference between this value and the previous value. So percent diff, I'll do it this way, percent diff SMX, and this is a percent diff DMX. So you already see on the first iteration here, there's a 4% difference in the stress. But the stress went up. 4 point, it was 42 megapascals, now it's 44. So just by having the element size, you're getting a 4% better answer, okay? But what we want to do is we want to keep going until we get a 1%, right? So this answer is approaching the exact answer. Let's go now to 6 inches. So again, just watch me. Don't do this. I'm going to clear all the lines out, size controls, pick the lines. We're going to do 6. Pick all the lines. Notice a little bit finer. We're going to resolve it. There you go. So now notice the contours are getting a little bit smoother now. Stress max is now 0.454 e to the 8th. 0.00448. So we're getting 2.6% difference. We want this value to be 1. I'm going to go another iteration on this. So here's the next one, 0.460 e to the 8th, 0.004489. So we're like 1.3% difference. We can actually go one more time to get exactly, or get it below 1%. And we'll call that converged. So let me do it one more time. Meshing, clear mesh, lines. All the lines, size control, all lines, 1.5. So there's the mesh. Solution, solve. .463 e to the 8th. Oh, shoot. 0.00449. There we go. So we got 0.6% difference. And if we actually take the percent difference between the original value, our 24-inch edge length, and the final value, it's an 8% difference. anybody who's an aerospace engineer is dealing with very tight safety factors. You could be under predicting your stresses, by 8% if you don't do a mesh independent study, which could be considerable. So it's always important to do mesh independence when you're running finite element simulations, if you can do them. Sometimes when you have extremely large models, you can't actually do this type of study, in which case you just have to have confidence in your finite element model results. But typically most models you want to do this. This is kind of a scary realization for people who maybe have used finite element analysis and just kind of use the default mesh and SolidWorks and went with the result, right? You could be off by 10% in terms of your stresses or more. All right.